Hello everybody, and welcome back to part 11 on generating functions. And in this video we want to prove that the nth Fibonacci number satisfies this crazy condition, that the nth Fibonacci number can be expressed in terms of this summation. So one thing to note is that uh, if you were to plug in 0 into this, you don't really get 0. So we're just going to be assuming that n is a natural number, so n is greater than 0. And another note is that, let's say we just plug in 1, right? Here we would get 0, choose 0. 0, choose 0 is 1. And we know that f sub 1 is 1. So we're just going to assume that if something is negative, um, then we're just going to call it, basically we're going under the assumption that if you have something choose 0, it's 1, and if you're taking 0, choose something. Basically, if you're taking something, choose something that's too big. So -1, choose 1, or 0, choose 1. Those are all going to be 0. And I guess that applies if n equals 0, because you get, well, no, never mind. But yeah, so for the most part, we're going to be dealing with n is greater than 0, and we're going to assume that if k is greater than n, so k greater than n, then n choose k is 0. That's the assumptions we're going to be working under. Okay, so let's figure out a way we can prove this. And obviously, this is in my generating function series, so we're going to use the generating function. So since I'm dealing with f sub 1 and higher, I'm going to use the generating function that corresponds to that. So if you recall, the normal generating function starts out, it doesn't have a constant term, or its constant term is 0 because f sub 0 is 0. But in this one, we're going to be starting with 1 first. And so that generating function is 1 over 1 minus x squared. So now notice that I factored out the negative here, and we see we have something in the form of 1 over 1 minus y. So we can apply the geometric sum. In other words, right, we're going to we have something in the form of x plus x squared to the n, and we're summing that over 0 to infinity. So what we can do is factor out, because we notice that x plus x squared, that's just x times x plus 1. So we can factor out an x to the n like this. And so now the trick here is actually reminiscent of something that we'll do more often later in the series, but I'm not going to get into the details here. But we're going to replace x plus 1 to the n with, well, this is just the simple binomial theorem, right? And n is a non-negative integer, so it's just the normal binomial theorem. And so what we get is, so instead of x plus 1 to the n, we now have the sums, k goes from 0 to n, of n choose k times x to the k. So I've just used the binomial theorem here. So now we have a double sum, and furthermore, we have that that x to the n is a constant in terms of this sum, right? Because right now we have x to the n is outside of the sum, so we can actually bring it inside of the sum. And so what we get if we do that is, so we have the double sum here. Oh, hold on. The double sum as n goes from 0 to infinity and k goes from 0 to n of n choose k times x to the n plus k. So here I've multiplied these two x terms together. And so now we notice, or we sort of want to grip on like what kind of things we'll be getting here, right? So, and what I mean by that is, what are the ordered pairs n choose k we're getting? Well, clearly by the bounds on k, we necessarily have that n is greater than or equal to k. right? But what if we sort of generalize this? What if we said that k was greater than n? Then we said here that if k was greater than n, then n choose k would be 0, right? So if we allowed for all non-negative uh, ordered pairs of n and k, all of them, not just n is greater than or equal to k, but all of them, if we extend our range, then it won't matter because n choose k is just going to be 0. And if we're extending our range, then n plus k, right, we can just take cases. So let's say we fix j. So we have some fixed integer j, and we want to look at j is equal to n plus k. Then sort of another way we can look at that is that if we have n, then k is just j minus n, right? And so our power of x will just be x to the j. But now, what will our coefficient be, right? We basically want this as one, now we just want one sum in terms of j. J, the smallest j can be is 0, right? Because if that's n and k are both equal to 0. But j can go to 0, or can go to infinity as a higher bound. And we know that we can make every other integer, non-negative integer value of j because if we just thinking about k is equal to 0, if k was 0, if we just looked at k equals 0, then we know that j equals n. And since n goes from 0 to infinity, we certainly have j is from 0 to infinity. So we know that every single value of j can be reached. So now we have x to the j. Now we just have a single sum. And what we're doing here, notice what we started with. We started with the generating function for Fibonacci numbers, which is just a single sum of polynomial terms times some Fibonacci number. So if we can find the coefficient of x to the j, then we can find what our Fibonacci number is, what our nth or what our jth Fibonacci number is. And so we notice that the sum, right? Imagine expanding this out, right? And you get some, you'll get quite a few, I think like n plus 1 or something, or j, some amount of binomial coefficients times x to the j, right? There will be multiple x to the j terms. But what happens when you collect all of them? Well, notice that since we've extended our range, right? So we basically have extended this to, instead of just going to n, we just have k equals 0 to infinity, right? And so this double sum means that we have all possible n and k, non-negative n and k. And since n plus k is fixed to be j, then our coefficient is just the sum of all the binomial coefficients with indices that add up to j. So let me write that. All right, so the coefficient is just the sum of the binomial coefficients that sum to j. So now we want to bring back what we originally had, right? This was the power series for f, for the Fibonacci numbers. So let's say j goes from 0 to infinity. So here we're equating generating functions, right? And so the x to the j term, right? Think about just j equals 0, right? That's the constant term. And we said that this would be, we're starting with f sub 1. So this is f sub j plus 1. In other words, we know that f sub j plus 1 is equal to the sum of the binomial coefficients that sum to j. So if we shift indices, we know that f sub n is equal to the sum of the binomial coefficients or that, I guess I didn't word this properly. They're two components summed to 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 j. So if we just subtract this by 1 and subtract this by 1, then our general statement is that the nth Fibonacci number, f sub n, is the sum of all binomial coefficients that have indices that sum to n minus 1. And here we see that each time our top index goes down by 1 and our bottom index goes up by 1. In other words, the sum is never changing. The sum of these two is always going to be n minus 1. And that's exactly what we proved here, is that we proved that f sub j is equal to the sum of binomial coefficients that have components that sum to j minus 1. So this was, it's kind of hard to explain, and we kind of extended our sum here, but we reasoned that because if k was greater than n, we knew that this was 0, so we just wouldn't have a term there, basically. So we could extend it and allow for this argument. So we could allow for this expression. Anyway, thank you for watching this video. I hope you liked it, and I will see you in the next one.